Now that we know load on a diaphragm typically goes to the nearest supporting member, we can idealize the resulting loads on the supporting members. Loading on the diaphragm is pressure, but the idealized load on the supporting members is a distributed load, also called a line load. To see how pressure becomes a distributed load, let's look at this example diaphragm. This panel behaves two-way, so the dividing lines create triangular regions on the ends and trapezoidal regions between them. This other panel has an aspect ratio greater than 2, so we can treat it as acting one way, and the dividing line runs this longer distance. Each region sends its pressure to the supporting member in that region. Mathematically, we are integrating the pressure to obtain the distributed load magnitude. It might be easier to understand by envisioning an example strip of diaphragm in this region. All of the pressure on this strip of unit width gets carried to this member. Integrating uniform pressure over this strip is the same as multiplying the pressure times the area. The area of the strip is a unit wide and has a length we call the tributary width. Based on just units, the loading on the supporting member is pressure times area per a unit length, which is force per length or distributed load. To calculate the magnitude of the distributed load, we only need to consider the pressure, P, and the tributary width. One way to think about tributary width is the longest distance load must travel in a region to get to the nearest supporting member. We can visualize the shape of the idealized load on a supporting member by looking at the region being supported by that member. For example, consider beam A1, A2. At the ends, the tributary width is 0, so the distributed load magnitude is 0. The distributed width increases linearly until midspan, where it reaches its maximum. Therefore, the distributed load increases linearly to a peak at midspan. The magnitude would be the pressure times this distance. Notice that the shape of the distributed load is the same as the shape of the diaphragm region. Now consider beam B1, B2. This supporting member carries a triangular region from the left in this plan view and a rectangular region from the right. The tributary width at the ends is the distance from the rectangular region. The tributary width then increases linearly to a peak at midspan. The peak tributary width is this distance from the apex of the triangle to the dividing line of the rectangular region. The result is this distributed load on beam B1, B2. Again, the shape of the distributed load is the same as the total diaphragm region carried by that member. For beam C1, C2, the tributary width is constant along the region, so the resulting distributed load is constant along the beam. Everything we have shown so far has been the idealized load due to just uniform pressure on the diaphragm. That works perfectly for live load, uniform snow load, or wind pressure on the roof diaphragm. For dead load, the supporting member gets loading from the diaphragm and its own self-weight. That self-weight adds to the idealized distributed load. So for beam A1, A2, if we want to determine the idealized dead load, the ends have no tributary width, but we have the self-weight. As we move to the middle, the tributary width increases linearly and adds distributed load to the self-weight.